Okay, hello, good evening, guys. Happy Thursday. Welcome back to our September week 3. Right, this is the third week of September, so we are going to finish our chapter 7 today. Right, so guys, we are towards the end of chapter 7. This is the third week of this thing, and I wish to finish this by today. Right? Why? Because next week, we are going into the nuclear chapter, which is much more interesting, which is going to be much more interesting. Okay, so this chapter, let's just be done with it lah, because you know that it's a very boring chapter. Okay, so guys, what have we learned last week? We did learn that the 3 types of energy. Okay, I think we mentioned the 3 types of energy. Yes, hello Martin. So we did learn that what is GPE, gravitational potential energy, or TKG in BM, tenaga keupayaan gravity. That would be the energy inside you when you are above a certain height. All right, so the formula is mgh, mass times g times height. G is always 10. All right, told you this already. And then what is our EPE or TKE? Elastic potential energy, tenaga keupayaan elastic. That formula would be 1/2 Fx. So F is the force, X is the change in length. All right, the spring, whether it becomes shorter or longer, that's the X. And then we have our kinetic energy, which is the energy moving one. So you have 1/2 mv squared. Okay, so these 3 formulas, you should know how to use it. Should you memorize them? I think they will give you an exam. I think lah, they will give you this in exam, but you need to know, all right, how do you use that? All right, so let's talk about conservation of energy, right? This one, I think I kind of, talk a little bit about this last week already. So we did say that energy cannot be created, cannot be destroyed, right? I think I told you this last week. Okay, so if you are at the ground floor, if you spend 200 calories of chemical energy, that means your food, you burn your food and you climb the stairs to 18th floor, let's say you burn 200 calories. So at the top, you will get 200 calories of GPE, theoretically speaking lah. So you should have 200 calories up there. And when you jump down, you have 200 calories of KE, okay, kinetic energy. And when you smack the ground, you should get 200 calories of sound energy. All right, I mean, you don't exactly get this lah, but what I'm trying to say here is, guys, energy cannot be destroyed, energy cannot be created, because at the end of the day, you still end up with 200. Do you get any extra or less? No. Okay, you don't just generate energy out of nowhere, and you don't just destroy energy into nowhere, because it doesn't happen. You will always get back, the same amount of energy. So this is what I'm trying to explain here. Okay, guys, understand? So if you do, let's talk about our pendulum. I think I mentioned this last week, right? A little bit lah. So let me just repeat this again. So let's just say you are at the top. When it is at the top, the pendulum should have maximum KE because you are at the highest position. Pendulum will be at the highest position when you started this thing, right? It is at the top. So now let's just say you have 400 GPE. Your KE now is 0. Why? Because your speed is 0. GPE, we are looking at the height. So now you are at maximum height, you have maximum GPE. You have 0 speed, so you have 0 KE. Makes sense, right? Okay, makes sense, right? And then as you swing down, you slowly decrease in height, you slowly increase in speed. That means your GPE is going to go down, your KE is going to go up. So by right, at the middle of the way, okay, in the middle of the way, you should get GPE 200 and KE 200. Okay, half of the energy, it's gone to the other energy. So when you reach Y here, you should get GPE 0, KE 400. So now all the energy from GPE is now converted into KE. Alright? It's just like two accounts, guys. You have account A and account B. Let's say you have Maybank and Public Bank account. You transfer 400 from Maybank to Public Bank, you still end up with 400, right? And then when you transfer from Public to Maybank again, then you still get 400, right? Money doesn't just disappear. Okay, money doesn't just disappear. It's like, okay, your dad paid taxes, right? Your dad paid taxes, right? Okay, every year. So if let's say your dad earns 10,000 every month, let's say lah. So at the end of the year, he should get 120,000. Okay, 120,000. So the government will charge tax according to your annual income. That is 120,000. Right? So if they read your account, they get 300,000, that's 180,000 more. You don't just say, oh, I don't know, the money just appear out of thin air, I don't know. You thought you're Najib, You thought you're Najib, He said, oh, that $2.6 billion, the 2.6 billion ringgit, suddenly got transferred into my account, but I returned the majority share of it. Okay, the last time I checked, when people want to do something to my account, they will take money out from it, not put money in. Okay, maybe it's lucky, I don't know. Okay, but I'm not Najib, so I don't know. Okay, anyway, so same concept here, You don't just get money out of nowhere. Money just doesn't just disappear out of nowhere. So you get what I mean, So when you swing back up, you will get back GPE 400 and KE 0. So now I convert back, I change my KE back into GPE. So as I swing up, my height goes up, but my speed goes down. You see, just now I swing down, I become faster, I become lower. Now I become higher and I become slower. It's like fast, slow, fast, slow. So this thing will repeat again and again and again and again. All right, so can you see, okay, let's say the middle here is also GP 200, KE 200, right? So at no point, you get less or more than 400, you see? Total here, 400, total 400, total 400, total 400, total 400. So at anywhere, the total is still 400. Okay, you don't just get one more or extra. Okay, I hope this makes sense, guys. I hope this makes sense. All right, so the next one, this one is the same concept, It's just that I use EPE because now I use Spring. Same concept. All right, so guys, okay, let me come back to here. Do you notice there's a bug here with this setup? Do you notice the energy here has a bug? Okay, anyone? Are you guys still with me? Are you guys still with me? I hope you guys are still with me. Okay, I know it's a very boring chapter. Okay, I hope you guys are still with me. Okay, so there's a bug here. Okay, so what do I mean? You see, I have 400 here, right? And I have 400 here. I have 400 here. So that means this thing, right, will just keep going forever. Does it make sense? Does it make sense? Does it? Okay, if you set up a pendulum to swing, let's say you do it today, and you leave it there, and you come back tomorrow, do you still see this thing swinging? Okay, do you still see this thing? You get what I'm trying to say here? Let's say now you set off this pendulum, right? Get this thing start swinging. Yes, Nicholas, hello. Okay, we are in page 8. So do you see this thing swinging, right? Today, okay, and you don't catch out that or anything. So tomorrow when you come back, do you still see this thing swinging? Because according to our concept here, it does, right? Because 400, 400, and 400, right? Right? So will this thing keep swinging? You see, see, that's the weird thing, right? You might say, sir, it doesn't. This thing will somehow stop, right? But according to this concept, it doesn't stop, you know. You still get 400, 400, 400, 400. It will just keep going forever. So does it make any sense? No. No. What are we doing here? This is assuming this is a closed system. Okay, system tertutup. It is a closed system. What does it mean? That means the system has no external force. No external force. What does it mean? That means there's no friction. We assume this place here is a utopia. It's a perfect world. It's, you know, a perfect world where, you know, it doesn't exist. Okay, we assume that there's no energy loss to the surrounding, there's no friction. So does it happen? No. Okay, this is perfect world where I will always get back 400. Okay, maybe this is just the first swing, right? Maybe. Okay, so this will only happen, guys, listen, this will only happen in a perfect world. Okay, like how you like your crush will like you back. Doesn't happen, isn't it? Oof. Okay. Okay, I teach science lah, right? Why do I still have the personal attack here, right? Okay, so it doesn't it now like gonna violate. Right. So this is not a perfect world, right? Okay, because the person you like normally doesn't like you back. what you right. Anyway, guys, so this is not perfect. So when you do this experiment, right? What's gonna happen is when this thing swings down, you will get 390. And then let's just take for example lah. And then when this thing swings back up again, you get 380. And then you say, aha, you say, sir, you see, sir, you lied to me. You say energy can't be destroyed. So where's the 10? Where's the 10? The energy is not destroyed. It's just that it is lost. Lost where? Because you have friction with air, right? When the ball comes down, there's the friction with the air, right? So when there's friction, you have heat. All right, so maybe along the way, right, 10 energy, 10 joule is lost to surrounding as heat. Because there's no such thing as no friction. Let's be real here. So this thing, eventually this thing will slow down because it's losing energy to the surrounding. All right, it's just like your Newton's pendulum lah. You know it's Newton's pendulum. You know Newton's pendulum? This thing, oh, not Newton's, okay. God damn it. Okay, Newton's pendulum. This thing, right? This thing doesn't keep going on, right? Okay, it doesn't keep going on, right? This thing will eventually stop, right? Because between the balls, the balls. Okay, so between the balls, there's friction. Okay, so there's friction, so there's a little bit, tiny bit of heat. All right, not to mention, when this thing goes on, right, you hear tick, 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 tick. So some of the energy is lost as sound. Okay, so this thing doesn't go on forever. All right, I mean, it does go on for a long time, but eventually it will slow down because heat is lost, sound is lost. So eventually it will slow down. Okay, I mean, if this thing goes on, if you set this thing off and 3 months later this thing still goes on, I suggest you go and get an exorcist, because your place is freaking haunted. I'm just saying, okay? I'm just saying, how can this thing keep going forever? All right, it makes no sense. Okay, call the priest. Goodness me. Anyway, so as you can see, our law still applies here. Energy is not destroyed. It's just that it doesn't stay in the system. It's lost to the surrounding. Okay, so you get what I'm trying to say here, lah. So anyway, So as you can see, my point here is, guys, my point here is energy cannot be destroyed, energy can only be converted. And in this case, we assume conversion of energy is 100% perfect. I mean, assume lah. Okay, we assume lah. All right. So anyway, let's go to our exercise, shall we? Let's go to our exercise. Okay, so this is where we apply our 3 energy here. Okay, yes, Savannah, hello. Anyway, let's start with this. So the length of the spring in the toy pistol is 300 mm. If a force of 5 Newton is used to compress the spring until it becomes 50 mm, calculate the maximum speed of the plastic ball of mass 50 gram when it's fired. All right, so guys, before we start doing this, right? Let's understand first what energy is here. Guys, what energy is being converted to what energy here? Can anyone tell me? Can anyone tell me? I compress the spring, then I shoot the bullet out. What energy is this? What energy is converted to what energy? Anyone? Okay, when I compress the spring, now what energy is this? This is EPE, right? All right, EPE, right? And then when the spring fires, my bullet, which is the plastic ball, flies out, right? So when the ball moves, this is KE. All right, so I'm converting EPE into KE. All right, so we can write it this way: EPE equals to KE. All right, we assume 100% energy of EPE from the spring is fully converted into KE, just like our perfect pendulum here. 400 GPE is fully converted into 400 KE. That's a big assumption, all right? But you might say, sir, how can this be possible? This is real life, right? There's heat energy in the spring. And then when the ball flies out, there's friction between the ball and the gun barrel. How can this be perfect? But we just assume it is perfect because there's no way for us to know how much energy is lost, right? We will not know how much energy is lost here and how much energy is lost here. We have no idea. So we just assume everything is perfect. All right, so EPE equals to KE. So according to our formula, EPE is 1 over 2 Fx. Right? This is what you learned last week. And then what's the formula of KE? Formula of KE is 1 over 2 mv squared. So this is why last week what you learned is very important, because now we are applying it in, practical situation. So now you have 1 over 2 Fx equals to 1 over 2 mv squared. So according to your linear equation, we can cut this away, right? Basic maths, guys. This is basic maths. So let's just stop everything in. So what's the F? What's the F? F is 5 Newton because I use 5 Newton to compress the spring. So this is 5 Newton. And then what about the X? The X, what is the X again? Okay, what is the X again? X is the change in the length of spring. Right? So you change your spring from 300 mm into 50 mm. So X would be 250 mm. But hang on, you cannot use mm. All right, you cannot use mm. Now, why leh? Because we have to use SI unit. You see, that's the annoying part. Guys, next year, when you go physics, you do the exact same question. Okay, you do almost the same question. And very annoyingly, in that question, right, they will give you all kinds of non-SI unit. So you have to very annoyingly, you have to convert that to SI unit. I mean, that's the challenge lah. Okay, so you have to remember what is SI unit. So in this case, 250 mm is 0.25 meter. Please don't tell me you don't know how to convert this, please. Okay, so 0.25 here. Okay, and then what is the M? M is the mass of the ball here. So the mass is 50 gram. So it's 0.05. What we are trying to find? We are trying to find the speed, which is V squared. So V squared equals to 5 times 0.25 divided by 0.05. And let's just throw this square here lah. This will become a square root. Okay, so what's the answer? What's the answer? I don't have a calculator here, so anyone can please press the calculator for me. Okay, guys, are you sleeping? Please don't. I know it's very boring. Just bear with me for one more week, guys. I swear, next week will be a whole new chapter. Okay, because next week we will talk about nuclear. Okay, so V is 25. You mean square root 25? Square root 25. So this should be 5 meters per second. Okay. Next week we'll be talking about radiation. Okay, we'll be talking about radiation. Is Wi-Fi radiation dangerous to you? Okay, will you die by sleeping right beside a modem? You know your Wi-Fi modem. Will you die sleeping beside? We shall find out next week. Okay, next week will be a very interesting chapter, as I said. Right. Anyway, so this is 5 meters per second. 5 meters per second. And guys, this is the maximum speed. This is the maximum speed. Will you ever reach this speed? No, because this is assuming the gun is 100% efficient. There's no energy wasted. Only you can reach 5. Okay, I mean in real life you won't, because some energy will be lost as heat in the spring. Some will be lost as sound. You know, when you pull the trigger, the spring will have the tang sound. Okay, some energy is lost as sound, some energy is lost as friction, as heat. So you will not reach 5. Okay, this is the theoretical value. It's like your exam. The theoretical full mark is 100. Do you ever get 100? If you do, then good for you lah. I mean, that's not a very frequent occurrence thing, right? So that's the theoretical full marks. Okay, by right, you study, you should get all 100, right? But that's wishful thinking, isn't it? That's just, you know, a perfect world scenario. Okay, it doesn't exist. So you will not reach this speed. Maybe you reach half. Okay, so that's they ask you already. State an assumption. What are you assuming here? Okay, you assume that no energy is lost to the surrounding. Okay, tiada tenaga hilang ke persekitaran. No energy is lost to surrounding, which is not possible lah. Like I said, which is not possible. There will be energy loss. All right, it's like a gun. Okay, guys, let's talk about a gun. Let's talk about a real gun. All right, so does a real gun use spring? Okay, so I know this is very boring. Okay, let's talk about a real gun. Guys, any of you interested in military engineering? Any of you interested in how a gun works, the anatomy of a gun? All right, a gun, a real firearm, they don't use spring. That would be a very shitty gun. Okay, your gun doesn't use spring. If you take apart your real gun, okay, let's say you have a Glock pistol. You know what's a Glock? You will not see a spring. So what do you see? What do you see here? Yeah lah, you still see a spring lah, but that's to return the gun barrel back to original position. You should see. Okay, let's just say a bullet lah. Okay, let's just say a bullet. Okay, this is a bullet. Okay, let's say this is a 9mm Glock pistol bullet. All right. So when you are firing, okay, let's talk about the anatomy of a bullet. A bullet, you only fire the front part out. The front part is the projectile. Okay, this is why when you watch movies or whatever, when they gonna shot, right, and then when they dig out the bullet, it's usually this small. All right, because the only part, the part that flies out is this. Okay, So what about the behind here? The behind here is the casing. It's the casing, and inside here there's this black color powder, what we call gunpowder. Okay, we call it gunpowder. Okay, or some they call it the salt of battle. Okay, salt of battle, which is gunpowder lah. So in this bullet, right, at the behind here, there's the thing called primer. So what happens when you pull the trigger? There's a hammer in the gun that will hammer onto the primer. Then the primer will light up. So this thing will start a fire. So when there's a big explosion inside, it will push your bullet forward. So in this case, we are not using EPE. In this case, we are using chemical energy. Then we convert it to heat energy because there's explosion. And then this heat energy will turn into kinetic energy. That's how your bullet flies out. All right, and this casing will get ejected from the side of the gun. This is why when you shoot a gun, pang, 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 and then you hear the ding, ding, ding sound because the casing is being ejected out from the side. And please don't touch the casing when you just fire the gun because it's gonna be smoking hot, right? Because this is a very big explosion. Okay, so is all energy converted into heat? Sorry, is all chemical energy converted into heat? No, some is converted into light. When you see fire, when you see a light, see a spark, and some is converted to sound. And I can say a majority part is converted into sound. That's why when you fire a gun, it's loud as hell. Okay, even a pistol, if you're at a shooting range, please wear your ear muff, your ear protection, because the thing is so loud. Okay, you just fire one magazine is enough to make you not to say deaf lah, okay, but you will impair your hearing for the next few hours. Not even joking, because there's a lot of energy right there. Okay, and of course, then how people at war no choice lor, because at war, right, your option now is to survive. Okay, death or not death, that's another thing lah. Okay, so anyway, hey, when you're at war, right, bullet is the last, the bullet noise is the last thing you'll be concerned about, because right beside you there are the tanks. Those artillery are even louder. Okay, and then you have Air Force up there. It's even much louder. Okay, why is the sniper more loud? Good question. Okay, you use a bigger gun, it will be a bigger bullet, right? If you use a Glock bullet, that's a 9mm. Okay, we call it a 9mm bullet because the diameter is 9mm, so it's this big. If you use a rifle like AK or a M1 A4, the bullet is this long. If you use a sniper, well, it's longer because you need more gunpowder, so the firing range is longer. They can fly longer. Okay, how does silencer lessen the sound? Good question. The silencer is to disperse the sound away. Guys, when you put silencer on, right, your gun is still not silent, okay, because the majority of the sound, right, comes from the explosion at the nozzle here. So they muffle the nozzle. Okay, it's like a muffler. It's like your car exhaust muffler. You still hear something, but it's not that loud. Okay, so guys, do you know that the engine oil filter can act as a silencer? They can. Okay, so anyway, and of course, not all KE is converted into the forward motion. Some KE is converted to the backward motion. This is what we call recoil. You know, it's recoil, right? The bigger the gun, the more the recoil. This is why when you look at those let's say AK-47, right? You have the original version and you have the improved version. And you look at the improved version, it's just like there's more handle for you to hold on. You have the front handle, you have the back handle, and then you have this small little thing at the gun barrel there. Those are the things to reduce the recoil. Okay, you bruise your hand, yes. So the more those things are the side equipments, those are to reduce the recoil, because recoil will make you tired and it will reduce your accuracy. Okay, so the point is to reduce the recoil. Now, see, who says physics is boring? You know where to apply, then that's when things gets interesting. All right, funny enough, guys, this gunpowder is also a fertilizer. Okay, this is what we call salt of potassium nitrate. Okay, potassium nitrate. So last time they used this as explosive, and now we use it as gunpowder. And funny enough, this is actually a fertilizer. So you can say that fertilizer can be used to make bomb. You will learn this in chemistry next year. Your ammonia, right? Ammonia, which is your pee. You know, your mom asks you to pee on plants as fertilizer, right? That's how it works. You can take the ammonia in your pee and turn them into dynamite. Okay, dynamite or TNT lah, trinitrotoluene, which is an explosive. Okay, dynamite is different. Dynamite is nitroglycerin. That's different. Okay, not the BTS song. Okay. Every time I mention dynamite, there'll be people telling me, "Oh, so the BTS song." Yes, I know. Okay. Anyway, so when natural bomb producers, yeah, if you know how to, if you know what to do, okay, you can use your pee and make bombs. Right. Anyway, so next B. A durian is dropped from a height of 5 meters. What is the speed of the durian just before the durian reaches the floor? Okay, very good question here. So when you see height, this is GPE. When you see speed, this is KE. So I'm converting GPE to KE, right? Okay, I'm converting GPE to KE, assuming that that's 100% conversion lah, right? So GPE to KE, so MGH equals to 1/2 MV squared. All right, so when you cut the M away, so you don't need the M. So G is 10 always. Height is 5 meter. Speed is what we want to find. All right, so V here should be square root of 100. So you get 10 meter per second. Okay, this is easy. All right, so again, do you reach this speed? No, you don't, because there's air resistance. All right, guys, I have something to ask here. There's another bug here. Since we cancel the mass away, right? Since they didn't say the durian, how big is it, right? So can we say that a 1 kg durian and a 20 kg durian? Okay, there's no 20 kg durian lah. Okay, let's just say nangka, whatever. So I don't care what's the mass, since we cut it away, right? Does it mean they reach the ground the same speed? Okay, do they reach the ground the same speed? I don't care how big my durian is. I don't care how big the fruit is. The fruit will reach the ground at the same speed. Make sense? Not so much, right? You might say, sir, how is it possible? How can a strawberry falling from the tree and a durian falling from the tree, how can they reach the ground at the same time? Okay, it makes no sense, right? I mean, in your brain, it makes no sense. That means if I were to throw a strand of hair from the tree, and if I were to jump down from the tree, me and the hair will reach the ground at the same time. Make sense? Freak, no. But say, how does it make any sense? But you see, when we look at the formula, right? That's what it says. Mass doesn't matter. I don't care how heavy your fruit is or something is. I don't care how light you are still going to reach the ground the same speed. Make sense? No. Because the heavier thing will reach ground first, right? Right? If you jump down from a tree and you throw a strand of hair from the tree, well, of course, you are going to reach the ground first rather than a hair. So what gives? Does it mean this formula is wrong? No, physics is never wrong. Because there is something called air resistance. Okay, air resistance. That means when I jump down, I will reach the ground first because air resistance on me is not that much. Okay, if let's say I'm 75 kg, the air resistance is 1 kg, it doesn't make any difference, right? But when if I throw a strand of hair down, the hair is 5 gram, the air resistance is 5 gram, of course the thing is going to slow down, right? Because of the air resistance, which brings me to this. Okay, guys, okay, let me prove it to you. This fella, he really proved it. He went and he went to a there. Okay, if you are interested, you can go and read this thing. You can go watch this video. Okay, really interesting stuff. So what did he do? What did he do? So first, he do this experiment in normal air. Okay, in normal air. You see, makes sense, right? So he compared a bowling ball and feathers. So you see, of course, the bowling ball is going to reach the ground first, right? Because when there's air, the air resistance is different. Air resistance doesn't affect the bowling ball that much, so the bowling ball will drop at the same speed, okay, very quickly. But for feathers, because the air resistance is, big enough to slow the feather down, so the feathers, they will drop down very slowly. All right, but according to our formula just now, mass doesn't matter. That applies in vacuum when there's no air resistance. All right, when there's no air resistance. So he did this experiment again. He sealed the chamber and he drew vacuum out. And you guess what happened? The bowling ball and the feather, they reached the ground the same time. So our physics formula still applies. It's not wrong. Guys, physics will never be wrong. Okay, you cannot prove an equation wrong. It's an equation for a reason. Okay, so in my point just now, if you throw a strand of hair and you jump down with the hair, if it happens in vacuum, you both will reach the ground at the same time. Okay, that means as long as from the same height, I don't care how heavy you are as light as an atom, you are as heavy as a whale, you will reach the ground at the same time. Okay, that's when there's no air resistance. You see, physics is always right. Okay, physics is always right. So here we are assuming that there's no air resistance. We are assuming that we are doing it in a vacuum, in a perfect world. All right. So this law of physics will apply. Okay, I hope you guys understand. I hope you guys understand. You'll be explaining this in physics next year when you learn about gravity. Oh boy, you'll be having a lot of fun. Okay, fun. Right. Anyway, see, the figure shows. Okay, there's no figure here. Sorry. A stone weighs 20 grams. Is placed on a stretch band of a catapult. Okay, a catapult is like the thing you use to shoot birds. The elastic potential energy on the rubber band is 0.5. Calculate the height of the stone if the catapult is released 90 degrees upwards. So now I'm using EPE, converting into GPE. Because I stretch the band, that's the EPE. And then when I have height, that's the GPE. So they already give you, you see, they make your problem shorter already by saying that EPE is 0.5. So 0.5 here. GPE is MGH. All right, so the M is 0.02. Convert this to kg first. G is 10. And then H is what we want to find out. So 0.5 equals to 0.2 H. H equals to 0.5 over 0.2. You will get 2.5 meter. Okay, so 2.5 meter is the answer. Okay, guys, I hope you understand. I hope you understand. This ain't nothing difficult, guys. This ain't nothing difficult. It's just that 3 energy converting here and there. GPE, EPE, and KE converting here and there. That's all. Okay, guys. Let's go into our exercise. Okay. I mean, this exercise should be enough already, lah. But you know what? Let's finish our exercise. So last week we did not do any. Because the exercise for me I think it's pretty damn simple. This is EPE, okay, this is KE, this is GPE. Okay, you don't need to do this, right? Okay, now what's the GPE here? So MGH, M is 1.5. Okay, height is 75 cm, G is 10. Okay, like I said, please don't ever get this wrong in exam, please, because it will be really embarrassing. Okay, right. So let's go to the part where we learn today. Let's go to question 14. Okay, I'm just gonna pick a few and do. I'm not gonna do all. Let's go to question 14. So Marisa likes to play on the swing at the park. Figure 7 shows Marisa swinging on the swing. Alright, I just find this language really funny. Right, so from J to K, state the energy transformation when Marisa swings from position J to K. So from J, this is pendulum, guys. Alright, so you go from GPE to KE. Because you have GPE here, you're at the highest position. When you come down, you're the fastest. So KE. So dari tenaga keupayaan gravity ke tenaga kinetic. Yeah, I'm just the right short form here, guys. Okay. Alright, so from K to L, that's the reverse lah. You're going from KE to GPE. TK ke TKG. Right, whatever. So B, identify the decreasing and increasing form of energy as Marisa swings from J to K and K to L. Right, so as I swing down, what is increasing? My KE is increasing. I'm becoming faster. What is decreasing? My GPE is decreasing because my height is decreasing. All right, GPE is height, KE is speed. Now, so we have to ask, is my speed increasing or decreasing? Is my height increasing or decreasing? Okay, and then next, K to L. Okay, K to L. What is increasing now is the reverse. My GPE is increasing because my height is increasing. Okay, and then what is decreasing? My speed is decreasing. So that would be my KE. So it's the reverse. Okay, you do understand, huh? So C, at which position does Marisa have maximum PE? Maximum PE, maximum GPE, she's here. Because she is at the highest J. What about maximum KE? When you have maximum KE, you are the fastest, you should be here. Okay. All right. That means if you stand here and you're gonna kick here, it's not that painful. But if you stand here, she swings down full swing and kick at you, it's gonna hurt. It's gonna hurt. Oh, J and L, yeah, you can say J and L. I would accept too. Assuming this is perfect position. Assuming this is perfect position. Because you see, why don't I write L here? Because like I said, right, 400 GPE just now, right? When I swing here, maybe it becomes GPE 380 already. If you write L, right, later the teacher will argue, because this is not perfect work. She lost some energy as heat. So L is not the max. Because I have students kena like this. The teacher die want to nitpick this kind of. I mean, she's not wrong lah. She's not wrong lah because there will be energy loss to surrounding. But that's kind of an asshole for the teacher to do so lah. Okay, some of the teachers are assholes, so okay, I'm not gonna judge because some teachers they are like that one. Okay, some teachers they are like that one. They just like to nitpick the shit out of things. Okay, anyway, so D is the sum of energy stored in Marisa's body at position J the same as the sum of energy stored in position K? Provide your answer. So is her total energy here and total energy here is the same? Like I said just now, at here, right? GPE 400, KE 0. At here, she should be GPE 0, KE 400. So you can say yes. Okay, yes, the total energy is still the same. Okay, because energy is conserved. Okay, energy is conserved. Tenaga dipeliharakan. Okay, I think it's dipeliharakan. Or energy is not destroyed, not created. Tidak dicipta, tidak dimusnahkan. You can say that. You might say, sir, just now we say energy will be lost, right? Energy will be lost, right? This one you might get 390 KE here, right? Ah, yes, you can say that. So if your answer is no, I would accept too. No, because energy is lost to surrounding. Okay, dihilangkan ke persekitaran. Yes, because they didn't say that this is a perfect world. In the question, right, they didn't say this is, perfect situation. There's no friction in this world. Okay, your crush likes you back. Oof. Okay, I mean, if you like your crush likes you back. All the power to you. Okay, but doesn't happen to me. Okay, besides my wife lah. Okay, besides my wife. All right. Anyway, that's why guys have multiple crushes. Okay, if you are fishing with one stick, you get one fish. If you are fishing with a net, you get a net worth of fish. Oh God, what will the world become? I'm just saying, okay. I'm just saying, okay. The more shots you take, the more chances of succeeding. It's a numbers game, guys. Who's thinking now? See? When you yeah, exactly, Martin. Exactly. Okay. Shots on one. I'm just suggesting, okay. Later you don't say that girl called me a pig because I like multiple girls. Okay. Deserve a fish. Hey, my friend, I have a friend who does that, Okay, and what's the amazing thing? He juggled at one point 4 girlfriends at the same time. Okay, mission freaking impossible, man. But hey, he's the man. Okay, he went on to 4 dates with 4 girls at the same day, on the same day. Okay, so guys, you can do that lah. You can do that lah. But if you happen to fish on a psycho beach, she might chop your balls off. I'm just saying, okay? I'm just saying, some girls they're very vengeful one, you don't play, they will chop your balls off. Okay, don't say I didn't warn you, All right, anyway, let's go to question 17. You see, this kind of boring chapters, I have to go on these kind of shit talks to pull your attention. If not, you'll be bored to death, isn't it? Yeah, you kids nowadays. Okay, anyway, so this is a roller coaster game. Okay, so as you can see, the roller coaster goes up and then it comes down. Okay, so state the energy involved at point. Okay, let's look at point P first. When you're at point P, this is fully GPE because you're not moving. Okay, because you kind of take a pause at the top, right? Before you go, so you kind of pause there. So that's the GPE. And then as you come down, right, when you're at Q here, right, you have GPE and KE. Because now you are fast, but you are still at a certain height. So GPE is not 0 yet. You're halfway. You have half GPE and half KE. All right, just like my pendulum just now, you have 400 GPE here. Okay, you have 0 KE here. Here you have 200 GPE and you have 200 KE. All right, and then when you are at R, now you should have full KE. You should have full KE. Oh, what am I writing here? Why am I writing 2 GPE? So you should have 0 GPE. You should have 400 KE. Assuming that this is the perfect world, that you don't have any friction. But that's not possible, right? How can there be no friction, right? So let's just assume, okay? Because it's impossible for us to know the friction. Right, next. So Asvan and Mikhail are also joining in the roller coaster game. Given their mass and the car boarded during the roller coaster game is 80 kg. Guys, you look at this question, this is really funny. Asvan and Mikhail and the car, this way they add together, it's 80 kg. What kind of roller coaster is 80 kg? Right? Are they like anorexic or something? Gosh, I worry for them. Okay, so they move down the track that has a height of 10 meter. Okay, so calculate the energy at point P. So this is fully GPE, right? Fully GPE, right? So the formula for GPE is mgh. So m is 80. Mass is 80 what? G is always 10. Okay, G is always 10. Next year you go physics, right? Next year you go physics, right? G is not 10 anymore. G is not 10 because G is 9.81. They have to argue with that little 1 here. So when is rounding to 10, right? So there you go. Right, so H is 10 meters. Okay, 10 meters. So now here the GPE is 8,000. Okay, 8,000 joule. Alright, so calculate their velocity at point R. Okay, so at point R here, we are assuming that all the GPE is converted to KE. We assume, perfect work, everything is converted to GPE. So all these 8,000 GPE is fully converted to KE. Okay, so let's just assume 8,000 equals to 1/2. M is still 80, V squared. Okay, V squared. So the speed at point R should be 16,000 over 80 square root, which is square root of 200. Okay, guys, so what's the square root of 200? Anyone? What's the square root of 200? Should be 14 point something. Okay, I don't have a calculator with me. 14 point something meter per second. 14.142. Okay, Yushin, thank you. Okay, 14.14 lah. 2 decimal points would do. Okay, two decimal points would do. So do you reach this kind of speed? No, you don't. Okay, no, you don't, because this is assuming that there's no friction. Assuming that there's no friction. All right, so now can you see why roller coaster they have a weight limit? You know why they have a weight limit? Because when you're over a certain weight, there could be too much energy, then the roller coaster could be overshot. Okay, the speed will be too high. Because when you have too high of a mass, you have too high of a KE, you have too high of a speed there, then your roller coaster might just break. That's why they have a weight limit. Usually it's around 100 lah. I mean, guys, when you're at 100 kg, I'm not trying to discriminate against heavy people but 100 kg, that should be quite a dangerous weight to. Don't you think it's very dangerous for Asia anyway? So you don't see anyone in Asia, any Asian that is 100 kg, right? 100 kg is quite a heavy weight. Okay, so guys, you know what? I think this chapter, it's done. All right, so I will wrap this chapter up for today. Okay, thanks for staying with me. For those who are staying with me, okay, for those who fell asleep, guys, it's time to wake up. Okay, if you need to rewatch this because you fell asleep because it's too boring, I don't blame you. Okay, come and WhatsApp me, I'll send you the recording. Okay, so next week, please get your chapter 8 ready. We will go into nuclear. Okay, and I will let you watch a video about Chernobyl. Ooh. Interesting. All right, next chapter will be a complete new chapter. It will be a very interesting chapter. Okay, you shall find out next week. Okay, so guys, see you next week. Okay, have a happy Thursday. See you soon. Good night. Bye bye.